This is an organizing lecture for our home Earth unit in a survey of astronomy course. I've chosen materials this unit to cover Earth, our home planet. What's going on here? There are some properties about Earth that we are going to cover, just general properties of Earth, which encapsulates its tilt and seasons and that sort of thing. We're going to look at geological features of Earth, just properties of the composition and what's going on with Earth's surface and insides. We're going to look at the atmosphere, magnetic field, and plate tectonics, very important concepts for Earth being significant to us, contributions to Earth's shape and heliocentric models. We've been looking at cultures through time, how they studied astronomy and what they knew about astronomy. And this is looking at, when did we get to know more about Earth? And when did we switch over to the heliocentric model rather than the geocentric model of the cosmos? We're going to compare observational techniques and calendars. These are not consistent across all of the cultures on the planet. We're going to look at different diverse cultures, how they use these observations for agriculture and ritual, and identify and locate commonly used and recognized celestial objects. So I have a whole lesson coming up about the stars and the constellations during different seasons, what's going on there. And so all of this is covered in our materials for the unit that you'll be moving through. So just to highlight some of these topics, when I put this course together, this unit, I noticed across several different readings that I had went through that models of the cosmos were similar in different cultures, similar in cultures that were on different sides of the planet. That was very fascinating for me. For instance, the Polynesians, and you'll read about this in the Astronomy Across Cultures text, the Polynesians had model of the cosmos like this. There was just like different layers of the celestial sphere or celestial sky, and what was important to them was the horizon. So there's different types of horizons for them, which is very interesting. But then when I saw what was going on with the Egyptians, they have this idea of Nut. Nut was a heavenly dome. They saw Nut, the mother of Earth, as the heavenly dome, which was interesting, which is similar to me. It looks like a dome, right? And also the Mesopotamians, they had an idea of the Earth, the structure of our world, as domes, but also they had an underworld as well. It was very fascinating for me. And you can see through all of these, there's a geocentricity. There's Earth being at the center of these models. And even this stayed, as they made more and more accurate measurements in terms of numbers in the cosmos, they maintained that Earth was more at the center, that the sun went around the Earth. And you may be familiar or will become familiar with the sort of convoluted ways they made up theories to explain what they were observing in the sky and make it make sense. So we move into an era where we're systematizing, we're making accurate observations, and we're moving more scientific. Before it was observational, and not that it wasn't necessarily scientific in the way that we think about that they were studying systematically and they noticed observations and compared them. I'm sure they had theories. But as we move into classical antiquity, there's a prioritization out of the Eastern European area and Mesopotamia and Greek, right? Central Europe, Greek and Roman, for rational thinking. And prioritizing this scientific way, the beginnings of Western science, really. So interesting here, we can see that the circle was a very prized concept here, and they were really reluctant to give up circles. And not that circles aren't going to be important as we move forward, but they're not going to be as important. We'll learn that the Earth actually follows a slightly elliptical path. I'll talk about that in a second. We're covering observational astronomy this week. We're looking at cultural influences on observation. So cultural influences, when we think about just observations and then science, what is it that we observe? What do we think it's important to observe? How do we measure those things? Those all have cultural influences. And we're looking at the natural world. Like, what are the metaphysics of how did we get here? What is everything made up of? What is the structure of the cosmos? And so you look at that stuff in Simone. You can see that this picture here is from Simone. They looked at the fundamental elements of the cosmos rather than thinking in terms of atoms, molecules, and that sort of thing. There is a definite evolution of technology that can be observed. We have observational techniques of the ancients. The ancients had, they went by what they had. When I thought about this, I thought, well, it might be easy to have like a stick. Let's say I live in one spot and I have a stick, and then I just keep that stick around in different points throughout the year. I notice like how high the sun is above a certain point. And so I don't necessarily need a measurement, but I can make comparisons throughout the year. And so observational techniques, I'm sure, were various and useful to those people. Polynesians actually look for specific sequences of stars when they're sailing across the ocean and they have no geographic references. The sky is the only thing, and they'll look for sequences of stars. As they go more towards the horizon, another star would come up and they would have a sequence of stars. And then they measured with their hands. They could say like one finger or a whole hand above the horizon, and that's how they did directions, and that's how they made measurements. But we moved towards more and more accurate measurements. I would say this is in the scope of Western science with classical antiquity. Actually, the armillary sphere was invented in 4th century BC, so 300 BC. Actually, this was in China. China came up with the first sphere, and if you can imagine a sphere in the middle, but then it has a bunch of axes that it's allowed to rotate on, that was started in China. And then from there, we believe that the astrolabe, all right, the astrolabe, which is a 2D armillary, developed from that armillary. So this over here is an astrolabe. I put a picture over here on the right. This is an astrolabe. Astrolabes were used for a very long time to make very accurate measurements in the sky in Greek and Roman times. And you can see in the Renaissance too, towards that era. So an astrolabe, I do believe I have a video how to use an astrolabe, and it is a sky map. It really is a sky map. You can get different templates, sky templates to put into the backside here, like this backside here. There's different templates, so if you're at different latitudes on the earth, you would need a different template to know where the stars were. And each one of these points on here is a star in the sky. All of those kind of point at a star in the sky. So an astrolabe is a very interesting thing, and so you can see that they're really trying to systematize and make very accurate measurements. This was enhanced by optics. We got better and better optics in the first telescope that came along, and you can see that this was almost 2,000 years later, 1608. That's AD. Current era, you could call it CE or AD, whichever one you're more familiar with, by Lippershey. And he was a Danish lens maker is what he was. And so he was able to create two lenses here. You can see a diverging lens here and a converging lens here. And so you can see things that are really far away. It magnified them. So the people who were astronomers were able to look farther away into the celestial sphere and see things that they hadn't seen before, or see things that they had seen before with more detail. And so we're getting more and more accurate measurements, and this evolution of technology that really propelled astronomy and is still propelling astronomy this day. Observational astronomy also encapsulates the geographic and environmental markers across cultures. So you may be familiar, I've noticed people are familiar with the Egyptians, and that the pyramids may be shaped according to different constellations and their orientation in different ways, or different holes in the pyramids point to a certain place in the sky. And so I'm calling these seasonal solar placements. They're tracking seasonal solar placements. Where is the sun in the sky throughout the year? There's horizon markers. The Aztec and Maya of Mesoamerica use different, if you live in one spot, you can go and put a big tower of rocks over on the horizon, and you can say, well, when the sun reaches that tower of rocks, then that's the winter solstice. That might be a measurement. So they're using their environment to mark things. They can use megaliths. Some people are familiar with Stonehenge and those sorts of structures. Buildings, you studied the Cahokia and how they oriented their buildings according to the sky, and other structures. So you'll study more about that this unit. So measuring Earth. As we move through time, closer to the classical antiquity, so we're thinking Greek, Roman, that time, all right, those people, specifically Aristotle, looked into what is the shape of Earth, what is the true nature of our cosmos. They figured out that Earth is spherical by watching a lunar eclipse. Very interesting how when we look at the shadow of the Earth on the moon as it moves past that in between the sun and the moon, the shadow of the Earth is round. And the only thing that has a round shadow is something that's spherical in space. So that's how we figured out it was spherical. So then there were different methods and people who went out to measure what is the size of Earth now. Now that they know the shape, what is the size? So measuring the diameter and distance to the sun, even how far are we from the sun? We knew that the sun was far away, but how far is that? What about the moon? How big is the moon? How far away is the moon? So those sorts of measurements happened at this time, and it wasn't accurate, but I think they did the best they could, and they came to numbers that were reasonable, and they weren't way off. They were off, but they weren't way off. Okay, so how they measured, for instance, the radius of the Earth by looking at the shadows of two different objects that were a distance apart on the planet. That's an interesting story. I think that you'll cover that, and I think that's an interesting story to know. As you move forward through the material, you'll look at Earth's geology. What is the Earth made out of? What is the structure of the Earth? Different geological features. Why Earth can support liquid water on its surface. If you're familiar with astronomy and studies in astronomy, we're trying to find water in different places in the cosmos. Not only because we're interested in, is there other life out there, but also, can we go colonize? Can we find water other than at Earth? Plate tectonics. Plate tectonics is an important feature of Earth. This was elusive to scientists for a long time in science and astronomy, that the continents actually moved on the face of the planet. So you'll study that. You'll look at the atmosphere of our planet and the magnetosphere. The magnetosphere is the magnetic field of the Earth. And there's a magnetic north and a magnetic south, and we can use a compass in order to figure out the direction. But that serves a larger purpose in regard to protecting the Earth and ensuring that our atmosphere and our surface is not bombarded by a lot of energy from the sun. So all of that has importance. You'll look at the importance of all those features of the Earth. Finally, I want to talk about the seasons and the tilt of the Earth on its axis. All right. The Earth rotates on an axis. It goes around one day. When it rotates on its axis, it's one day. And what we learned is this axis points essentially at the same place throughout the year. And you can see that on this picture here. The 23.5 degrees, the axis points towards our North Star Polaris. And the radius of our revolution around the sun is actually not that large. And so, large in the whole idea of the cosmos. It's kind of small, right? Because we're in a solar system that's in a galaxy that's in a, right, that the cosmos is huge. So in general, when the Earth goes around the sun like that, its axis generally points at the same star throughout that time. Okay. And what happens is that causes our seasons. I'm going to talk about this a little bit more, but what I want to highlight on this picture or on this slide here is that what I think people get confused about and that throws off their understanding of the seasons is that they'll look at a picture like this and they'll notice that the Earth is at different distances from the sun at different points in time. But what I don't like about this picture is it is not an accurate picture of the shape of the Earth's orbit. The shape of the Earth's orbit is nearly circular. So when people who don't understand that the Earth's orbit is nearly circular, when you ask them what causes the seasons, they'll say the distance from the sun, because that makes sense. If we have something hot here and we are a shorter distance from it, you would think, right, that it would be warmer. But that's actually not the case. That is actually not the case at all. What we're going to notice is that the Earth's orbit is nearly circular. That means it is approximately the same distance from the sun the whole year. So I can write that down. Approximately the same distance from the sun all year. All year. There's a little bit of difference. There is a difference. This is slightly elliptical, but it's mostly circular. Slightly elliptical. So it's the same distance from the sun the whole year, so that means seasons is not caused by the distance from the sun. Seasons are not caused by the distance from the sun. What is the seasons caused by? It's caused by the tilt of the Earth's axis. So let's look a little bit more at this. I use and will have assignments on an app, an online simulation. And again, the simulation starts out, this is its default setting, and it is looking at the side. Like I'm kind of looking at the side of the axis from the Earth. And I think students also get confused because this makes it look like the Earth's orbit is elliptical. But what you're going to need to do on this to really get a good idea of the shape of the Earth's orbit is to rotate it. You can click on it and drag it and rotate it, and you can see that the Earth's orbit is nearly circular. What I'm noticing here, and you can use the little key down here, this is the point where it's closest and farthest away from the Earth. You can see that. This red line says it's the summer and winter solstice, and this green line is the spring and autumn equinoxes. Spring happens here. Winter happens here. I guess I'll go this way. This is summer, and then this is fall, and then winter is here. So it goes in this direction, the counterclockwise direction here. And what you're going to notice is that it's farthest away in the summer. When the northern hemisphere, I'll call this the northern hemisphere, because that's where I am right now, hemisphere. When the northern hemisphere has summer, the Earth is the farthest away from the sun. When we get to winter, this is its closest. In the winter, the Earth is the closest. In the winter for the northern hemisphere, the Earth is the closest it ever is to the sun. Okay, so it's not a distance thing. Seasons are not caused by the distance. So when you're looking at this, make sure you've oriented it in the correct direction so you're not thinking elliptically, you're thinking more circularly. I have another app, a simulation that I have my students go through where it looks at the angle of sunshine on the Earth in different seasons. The Earth's axis, the direction of the spin, is pointing away from the sun. The sun is over here. This is where the sun is, over here. And it is shining light towards the Earth to the left. All right, so I like to put arrows on this. So light is coming in from the sun this direction. And this light hits, you can see across the surface of the Earth, the light hits at different angles. We have a 90-degree angle right here on the very right hand side of the earth, I'm going to use a color that you can actually see. There's a 90-degree angle there, but up in the northern hemisphere, it's a very shallow angle. Okay, so throughout the year, different parts of the earth are getting different intensities of light. And you'll be able to read that down here. You can read down here in the winter, all right, sunbeam inclination, 18 degrees. You can see that this would be an 18-degree angle. And so the direct horizontal intensity is 190 watts per meter squared. So in the winter, you're not getting as high of a wattage per unit area. So you can use the simulation to look at the angle of the Earth's axis relative to the sun and what effect that has on the energy reaching the Earth in different times of the year. I have this from your textbook, the OpenStax textbook. What we're looking at is, I do believe, the Tropic of Cancer. So you can see that there's a Tropic of Cancer. Tropic of Cancer is the line above in the northern hemisphere, above the equator, that gets 90-degree angle sunshine in a certain month. We can see that that would be summer. Right, summer or I will say June for the northern hemisphere. And you can see that that's where it receives the most direct angle of light. Down here, the Tropic of Capricorn, the Tropic of Capricorn is receiving 90-degree light. And that would be December. That would cause a winter in the northern hemisphere and a summer in the southern hemisphere. That's why the northern and southern hemispheres have winter and summer at different times of the year, alternating, opposite different times of the year. Okay, so what does this all come together for? Well, we have different calendars. Calendars became a key for human survival on the planet. Not only do we want to predict like migration and weather and when to plant our foods, right? It also directs our rituals during different times of year, especially if we worship gods or need to sacrifice or make prayers. So calendars have survival and cultural influences. Again, migration of game, weather, seasonal relocations. You may be nomadic and relocate. Agriculture, when to move or when to plant or harvest. Those would be indicators of changing weather. Tides are caused by the moon. I brought up this picture again of the moon on this 30,000-year-old artifact. And if you know the cycle of the moon, you'd be able to predict some tides and when's high tide and low tide, especially if you're a fisherman and collecting shellfish. And then also, there's different, when we think about calendars, there's different structures, developments, and uses of calendar. We can use astrological observations, actually looking at things in the sky. We could look at planets. We could look at stars. We could look at constellations. We could look at all that, not just solar, but the other celestial objects. And we can compare those celestial objects to geological or environmental markers. And I picked this picture over to the side. I love this picture over to the side here, where we have this path. There's some stairs, the path up to a square little landing up here. You can see that in the larger perspective here. There's a square landing up front. So this is looking towards the sun that way. I'll use a color you all can see. It's looking towards the sun here. So this picture is looking this direction here. And you can see that's a pretty extensive geological, like they built this. It's a structure that they built to be able to watch the sun, and when the sun comes up here, they had to make all those measurements and know exactly before they built that structure. So these aren't arbitrary, and these structures help them observe the calendar and engage in their rituals at appropriate times throughout the years. I added this up here because I really appreciate this quote here. However, calendar astronomy are not identical, since the calendar as a human creation constitutes as much a scientific achievement as a social system. I'm aware of multiple different calendars. You may be aware of a Chinese calendar as opposed to a Gregorian calendar. That we'll study those this unit. So it's a social system. Calendars are embedded within a social system. It's not necessarily scientific, it's a social system. The calendar is social life, and the effort of its elaboration consists precisely of seeking common denominators to be applied to the observation of nature as well as to society. Closely linked to the seasonal rhythms, climate, and agricultural cycles, the calendar imposes socially defined measure of time. When is the new year? When do we celebrate holidays? When is our solstice in relation to all of that? Regulating economic, political, and religious activities. So we're seeing how astronomy has such a significant impact on not just our survival, but as our civilizations on the planet, as human civilizations progressed, we had more sophisticated economics, we had more sophisticated politics, we had more sophisticated spiritual and religious activities. And all of that was mediated by these and recorded by these calendars and dictated by the calendars. So hopefully this lecture gave you a little bit of highlight for this unit, what to watch out for and what to pay attention to.